All right, welcome back to Lag Demon Programming. We're here in this video series talking about Scilab and Xcos and doing some modeling. We're going to soon be getting into control systems, which is what we really want to model with this so that we can do some stuff with the Raspberry Pis and control some things. And we need to learn a little bit about how control systems work, and we need to be able to model them so that we can ensure that we're going to be doing the right things with them from our Raspberry Pi. Now, the control systems in general are a process of taking some control input, doing some stuff to it, and causing something to happen in another system, in the system that we're controlling. There's a couple different kinds of control systems. We'll get into that later. I'll briefly talk about them now. They're called open loop and closed loop are the two major categories. They have different characteristics depending on what you're trying to do. We'll be probably working mostly with closed loop control systems, which provide feedback. A key point of any control system is the transfer function of the system that you're trying to model. Now, transfer functions are they're a mathematical model of the system that you're going to control. So the thing about transfer functions is they can be calculated depending on the type of system you're doing. More complex systems, oftentimes you do stuff to them and you measure outputs and you deduce the transfer function from that. And we might do some of that. The mathematical analysis can get quite heavy, but if you're interested in the math, we may do some on that in the future. I can be honest, I'm not heavily practiced in the math. I have done it in the past. But basically, the transfer function is a Laplace transform of the impulse response of a linear time invariant system with initial conditions equal to 0. That's a mouthful. And so I'm not going to go into detail about Laplace transforms, but I do want to point out one thing when we're building this next little model here. What we're going to do is build up an impulse response model so that we can see what an impulse response is in terms of a transfer function. And so let's get to building it, and I will explain what I mean by and why I brought up Laplace transforms. So I have here a blank canvas in our Xcos system. I am going to save it, and we'll call this impulse response. And I will put all of these files, these Xcos files, up on, that one got saved as Zcos, interesting. And so did that one. That doesn't matter, I guess. One's in zip format, the other one's not. So impulse response, we'll save that. We're going to build a very simple little impulse response model and take a look at its output and talk a little bit about what an impulse response is and why it's important to look at when you're doing system designs around controllers where you're trying to control things. So the first thing we need under sources here, we need several items. We need this step function. So this step function is going to provide our impulse, our step for our system to respond to. I said impulse response. It can be, in this case, we're looking at step response. They're very similar in concepts, but we're going to use a step. So I shouldn't have called it impulse response. I should have called it step response. Maybe I'll rename the file. We also need a scope, and we need a clock. So let's go ahead and grab our clock, and then I will zoom this so these are bigger. And of course, under sinks, we need our C-scope. This is standard. And then up here, under continuous time systems, we need this thing here, a CLR block. And that doesn't look too bad mathematically, but you'll notice there's an S in here, okay? So if you read the documentation, it will tell you that this is a polynomial that goes in here, and you can put a polynomial in, and I'll show you in a minute how we can adjust that, how we can set the polynomial to what we want. It's in a very special form, and they'll tell you it must be in S. Well, if you're not familiar with Laplace transforms, that's what that means. Okay, a Laplace transform takes a differential equation and transforms it from the time domain into what's called the S domain. And so the variable name changes from T to S. That's just a convention, but it's always used as S. And usually, in most circumstances, it can change that ordinary differential equation into an algebraic expression, which is what we have here. There is some differential equation in relation to time that this 1 over 1 plus s is a Laplace transform of. So this is our transfer function, but we're going to modify it. In fact, we're going to modify it right now, and then I'm going to have to go through here and set up some stuff. We're going to put the numerator as 2 plus s, and we're going to put the denominator as 2 plus 4 times s plus s raised 2. Okay? And now I'm going to move this over, and we'll expand this so that this looks a little nicer. And there's the transfer function we're going to do a step response on. And so again, this is still in the S domain. This is in proper form. In these kinds of functions, the numerator must be a lower power than the denominator, or a lower degree. So here, this is a second degree, it's s squared. This is first degree, it's just s. That's fine. We'll hook it up, and then we'll go through here and set some settings on all of these things. So I think simulation setup, we probably want to run this out to about 5 seconds. Scope setup, let's see what's our step. Final value, step time will start at 1, initial value 0, final value 1, that's fine. Under our scope, we just want this to be about 1.2 or 0 on the min, and max of about 1.2 should do it. Refresh period probably of 10. Simulation setup, let's change that. Let's put this back. Let's put this out to 10 as well. 10 seconds. And I think that'll do it, unless I made some mistakes here. Let me look at some things. That's fine. That's fine. What do we got here? Yeah, that's fine. And here, I'm just looking at my notes. Yeah, everything's fine. Okay, so let's save that. Just press Control S while this blue bar on this is highlighted, and we'll go over here and run it. So this graph is the unit step response of this transfer function with respect to time. So this responds to time in this manner, and it slowly approaches near 1. Okay, a couple of things you'll notice about it. If we come up here to about 66% or 63%, and we come straight across Oh, this should be 50% should be. Oh, that's a different equation. No, never mind about that. Oh, I'm starting at 1. That's why. You know what? I'm going to change that here. Let me close that. I'm going to change this. Come on. Step time. I'm going to set the step time to 0. So it starts at 0. And let's run it. There we go. And you see this climbs towards 1 over this 10-second period out to here. Okay. And 50% in this case is way up here. Or 50%. 63% is happening about here. That's the first. 63% is the first time constant of this curve. Anyway, we won't get into that right now. We can change this, and we can see quite a bit of different graph. Let's change this to 2 over 2 plus s. Oops, s. So this is just a first order. We'll save this and see what this does. It should still fall within more or less the range of this. So now we're much steeper. We're coming up much more quickly here. So this is the response, the function that forms that response. And what we have to do is figure out what that function is for the particular system we're doing. Now, sometimes if you're controlling certain things, if it's a product you're controlling, the engineers that made that product may have a transfer function. It could be in the technical specs, and it'll be in this kind of form. Or they might give it to you in some other form, which you have to then derive it. They might give it to you in the time domain, and you have to do Laplace on it. You can also collect data. This is sort of like taking a pendulum and whacking it and watching it swing, collect the data on it, and then work out the transfer function. So that's how you do a step response in Xcos. And we will use this as a tool to decide what we want the response to be, and we'll adjust this equation accordingly for our purposes. In most cases, we'll be able to get close enough by looking at the system's behavior and deciding how we want it to respond to be able to do that in a reasonable way. So yeah, that was my example one that I did to make sure everything was working. So yeah, to kind of find, I'm sorry, I got myself confused momentarily. Okay, so that's a transfer function, and just in brief, the importance of a transfer function is this: that eventually what we're going to do is we're going to build a control system, and I'm just going to use some user-defined functions here first. I'm gonna drop a couple in. In fact, actually, let's make a new palette here to talk about this. So why we were talking about the transfer function and the unit step response is we're going to start at some point in time building a system. Okay, and I'm just going to use these. I'm going to leave these as empty. We're not going to do anything with them. We're going to first use some transfer function to determine what our plant is, and this is the plant. And some of this may not make a whole lot of sense right now, but basically the idea of a plant is it is the thing you want to control. So if you're controlling a robot with some motors on it, the motors and their little controllers and whatever's inside or whatever comes with them is our plant that we want to control. We also then will have a controller, and this is the thing we're going to build that's going to control that. So this is the controller. So I'm going to label these. And over here will be some sort of input. So let's we can go to sources, and here's an in, right? So this is some sort of input, goes into there, this goes into there, and this goes to some sort of output. We'll go to sinks, and we should have an out F. Okay, and this is our output. Now, this is some control signal coming in. If this were a thermostat for your house, this control signal would be the set temperature, and this output would be telling the air conditioning to turn on or off, or the heater to turn on and off. So this is the output of the plant, or whatever the plant is doing. The plant is turning on, so this is just the output. And if this were an air conditioning system, this would be your house cooling down. The plant would turn on the air conditioner or turn on the heater, and it would cool off or heat up the house. That's the output. In this form, this is what we call an open loop system. There's no feedback. There is an additional way to do this, and I probably should make this just a little bit bigger so we can see it better. Another way to make this kind of system is to have a closed loop system. Now, an open loop system doesn't have any feedback. The input to this does not depend upon the output. But if you think about your thermostat, when the cooler comes on, the temperature cools off in the house, and eventually that temperature's got to tell this thing to turn it off. So what we can do there is we would have a sensor. So there's going to be, we'll go back to our control blocks. Oh, shoot. I don't know why the palette disappears like that. It's got closed somehow. We'll put another super block, and I'll show you another little trick here. You notice the arrows are going the wrong way on this particular block. I'm going to come here and hit Control R and rotate that this way, and then I'm going to right click on it because it looks funny like that, and I'm going to go down here to Format and Flip, and so it's the same direction as that, but the arrows are pointing this way. So this block here might be a sensor. So we would have a sensor. In this case, in thinking about a house, it would be checking the temperature of the house. And it's going to supply some feedback. And so if we go up here to mathematical operations, and we get this sum function, open this, and change this second one in here to -1. You'll notice we get a plus and a minus on this now. That means that it's you're going to take whatever comes in here and subtract whatever comes in here, and it's going to put the difference out. So we can delete this. Delete this line. Move this up here. This difference will now be the input to our controller. Our input here will be still the control signal going in here, but our sensor will provide an information to this about the temperature. So if we're putting in temperature here as an example, this says, oh, the temperature's high. It puts out a positive number. The controller sees that positive number, says, turn on the air conditioner. The air conditioner turns on and runs for a while, and as it does, this sensor sees the temperature coming down. And when that temperature comes down to where it's near this, the difference then becomes nearer and nearer to zero. It gets within a gap. Our controller has to take that into account, and it says, okay, controller says, fine, it's time to turn the air conditioner off. It's cool enough. Or it's too cold in the house. It turns on the heater inside the plant, which is the house, and the sensor picks up the temperature rising. When it gets within a certain range of this, the controller sees that difference, says, okay, the difference is small enough now, turns that off. So this is a standard form of a simple first order controller that uses feedback. There's more sophisticated ways to do this. There could be multiple controllers. multiple plants within controllers and so forth, and different feedbacks doing different things. There can also be multiple feedback loops doing different things, and we'll talk about that eventually. There's a special kind of controller. I'm not going to mention it right now. There's a special kind of controller that uses a number of feedback loops and a number of different ways of determining what the output should be altogether, and it's very powerful. So, that was my phone. So we're about 20 minutes into this video. I hope you enjoyed this video. If you did, hit that like button. If you really liked it, hit that subscribe button. And I hope to see you in the next video. Thanks for watching, and I'll see you.